In this video we're going to have a look at the XPS of cellulose using data from the Latrobe database. The cellulose polymer in principle has carbon in two different bond states with oxygen. That is to say, we've got a set that are bonded to oxygen in a single bond and then otherwise bonded to carbon and hydrogen, and then we have another carbon atom that is bonded to oxygen in two directions and with carbon in one and hydrogen in the other. And as a consequence, we'd expect two peaks. These two peaks should be offset in energy due to this chemical state difference, and we also have a significant difference in the number of atoms of carbon that are in the single bond with oxygen compared to the carbon bonded twice to oxygen, and so we should see a difference in the ratio of these peaks. And there are no other forms of carbon within this cellulose polymer. The Latrobe database includes a number of cellulose type materials, and one of them is designated as cellulose. These data were downloaded from the database, it's on the web, and they include survey spectra and a set of high resolution spectra taken at different parsenages. Looking at this survey spectrum, we can clearly see the oxygen peak and a carbon peak, and then the corresponding Auger peaks to these two photoemission peaks. So this is consistent with cellulose. However, if we look at the carbon 1s, what we see is a structure that is not consistent with what we were expecting, namely two peaks for carbon 1s, one more intense than another, so there's some consistency here, but we have a third peak which is clearly not either of the two peaks that we would expect for cellulose. And the binding energy for this, although it's shifted by virtue of the charge compensation, we would expect this lower binding energy peak to relate to a CH type signal. So what we have to do is understand why this peak deviates from what we expect for cellulose. And the way we'll do this is to consider these two carbon S spectra that were measured at different parsenages. Hence you find the intensity changes as a consequence of the different parsenages, but the resolution has not altered significantly. The underlying carbon 1s peaks are determining the resolution for these peaks more than the instrumental response or the change in the resolution as a consequence of going from parsenage 20 to parsenage 10. So at least as a means of testing what's going on with these data and trying to understand how these envelopes are formed, we can use these envelopes from parsenage 20 and parsenage 10 and the vector method to try and understand the shapes that are contributing to the deviation from what we expect from cellulose. The options for working out difference between spectra are on the calculator property page of this spectrum processing dialog window. And the button labeled different spectra applies to two spectra overlaid in the active tile, and it will create a new data file containing a sequence of spectra that are calculated from these two spectra, representing an evolution from the red spectrum to the blue spectrum. And the objective is to find within that data set spectral forms that we can identify with cellulose, and hopefully another spectral form that will show us the difference between cellulose and what we see in these two spectra. Before calculating the different spectra, the first thing we need to do is to make sure these peaks are aligned as best we can. And we'll use the calibration property page to achieve this. So what I'll do is I will normalize these data and then shift one relative to the other, so that I see this carbon peak here that I think is related to the CH type intensities, so these align. And I can do this by holding the control key down, and when I hold the control key down and I can slide the mouse, then you can see that an image of the red spectrum then slides, so I can then by eye choose an adjustment, and the adjustment in terms of offset is a rather small one. The values are calculated from the cursor actions And when I say yes, they're updated here on the energy calibration measured and true values. Using these two values, when I press apply, then the first spectrum that was selected when these two were overlaid, namely the pass energy 20, will be shifted relative to the one that is blue, that was the second one selected. So I press apply and we end up with a new slight adjustment to these data, and we'll preserve these by copying both of these VAMAS blocks in the process data form to a new VAMAS file. So now I have calibrated data, and these are two spectra aligned so that I can now use the options on the calculator property page to create different spectra. So a new file is created and a list of different spectra are now available to look at the differences between the two spectra that were overlaid in the active tile before pressing the difference spectra button. The idea is that these different spectra provide different perspectives of these data, and if we search through this list we can see how this peak here is diminishing as I slide down this list. We're ending up with a VAMAS block that contains a different spectrum that is starting to show 2 peaks rather than 3, and it's a question of deciding how much of these data we can eliminate one from the other. This peak here is not quite disappearing, but nevertheless that's a new shape that is consistent with having 2 peaks corresponding to a single bond with oxygen for the carbon and a pair of oxygen peaks bonded to the carbon with this offset here. So let's save that one. So I've got a new VAMAS block, which if I display I can then step across with the arrow button, and then that leaves me with a position within the list that corresponds to something that I feel more comfortable is relating to the cellulose. And so if we carry on going, we should find that we see different spectra. That this is a characteristic different spectra where you've got a negative going peak that is non-physical. But if we carry on down this list, we start to see the negative peaks becoming less pronounced and the positive peaks looking more like spectra. And here's one that, again, if I step around here, I've got a spectrum that might be characteristic of a CH type peak with some CO bonded carbon here. So I'll save that one, ending up with a pair of peaks. Let me turn off the normalization. Where one spectrum corresponds to a C1s spectrum where we have predominantly 2 peaks, and there's a peak here, but even Beamson and Briggs polymer database indicated there was some form of contamination of the cellulose signal. So that's not a significant problem for identifying this as cellulose. And then we have another form that represents a combination of a CH type peak. There's obviously some other oxygen bonded peaks here, and maybe another one. So maybe there are 4 peaks beneath here. So let's now see how these relate to the original data. So I'll copy these back to this file. These were both selected, so I can copy these to the file where I had the process form of these carbon 1s data that had been shifted. So if I display these 2 vectors that have been calculated, these are mathematical, which is why I'm referring to them as vectors, and then I see how these relate to the spectra themselves by using the generate spectra button and overlay a row of these. So you can see here, this is the pass energy 20 and how this relates to the data that we saw. So this is the red spectrum is being constructed from these 2 shapes that I calculated, and for the pass energy 10 You can see there's a lot more of this CH involved. So we could now interpret these in terms of carbon peaks and components. So using the quantification parameters dialog window, we'll go to the regions property page and create a background, and then we'll put in some peaks, make an adjustment to the width, let's say one more, and say fit. So we end up with a peak model that looks like we've got some kind of contamination that represents various forms of carbon bonded to oxygen, and various permutations of that. Whereas for the other spectrum, again simply putting in a fit based on, let's say in this case 3 peaks, and say fit, well, we've ended up with a pair of peaks here that might be deemed to be in the right proportion. That's 5:1. If I say fit again. So these component peaks that are fitted to a vector are indicating that we've got the right ratio for these 2 peaks for cellulose, and the offset is also about right for cellulose.